And since the first thing we're going to do is graph, let's go back to this slide and we'll go from there. But before we get started, any questions on anything we've covered so far? Okay. And then the follow-up, what I was talking with Charles about, I did get, or at least I hope I got everything up there on Blackboard. Your syllabus is there, the research paper instructions, my locator card, and the YouTube videos, and a few other websites that either I found or students have found and told me about, and I put them out there in case you find them helpful for the class. All right. Any questions? Okay. Middle of page 4, the little discovery here, it says graph the two lines. Here's the first one. Let me get my pen set up. 3x minus y is equal to 1. Now, if you were going to graph that, tell me, would you leave it like that, change anything? How would you go about graphing? Say again? Yeah, you could change that, or you could just start plugging in numbers. How would you go about graphing that? Okay, how would you rewrite it? A little louder. Y is equal to 3x minus 1. Perfect. What form do we call that? No, it's slope-intercept. Okay, and what can we tell from that? Okay, we know the slope of what? Second? Okay, and what is the slope of that line? Oh, that is a linear equation. You're right, okay. What's the slope? 3. What else can we tell? Okay, and where does it cross the y-axis? -1. Okay, so that's what we plot first. Where it crosses the y-axis, called the y-intercept, 0, -1. And then the slope of 3 tells us we go up 3 for every 1 to the right, up 3 for every 1 to the right, or down 3 for every 1 to the left. Because -3 over -1 is still 3. Down 3 for every 1 to the left. And there is the approximate, I don't draw straight lines very well, obviously, approximate rendition of that line. The second of these is, let's do this in a different color. What color would you like this one? Second? Red. Okay, we'll go in red. The second of these is 2x minus y is equal to 0. 2x minus y is equal to 0. Anything you would do to that one? Second? Okay, and what would that be? Oh, I thought I went to red. It didn't go to red. There we go. Okay, what would that be? Y is equal to 2x. Okay, can you give me some points there? A little louder. Through the origin, okay? So it goes through the origin, so there's 1 point, if I can get it to right, and then it has a slope of 2. So you go up 2 for every 1 to the left, and for some reason my pen's not right. Okay, there we go. There, and also down 2, 1 to the left, down 2, 1 to the left, down 2, 1 to the left. Now, this is illustrative of why graphing is not the best idea sometimes, because these lines have very close to the same slopes, 2 and 3, and so they wind up crossing each other, and my poor drawing, you can't tell where they cross, except we know that point right there was common to both of them. So the solution is 1, 2, okay? Where do they intersect? They intersect at the point 1, 2. Okay? How many solutions does that system of linear equations have? One and only one solution. That's it. Okay? Now, with the same first equation, we're going to change the second equation. Okay? So, if I can get it to eraser to come up here, we're going to change this to 3x minus y is equal to 0. That changes this, and it changes everything here. Or almost, well, yep, everything red. Almost everything. Okay. How would, this is 3x minus y is equal to 0, so y is equal to 3x. How would you graph this one? Say this again.
The same way you graph the 2x.
Okay, and always start with a point. What point do we start with? Origin, 0, 0, because when x equals 0, y is equal to 0, okay? But this time we have a slope of 3, up 3 for every 1 to the right, up 3 for every 1 to the right, or down 3 for every 1 to the left, or down 3 for every 1 to the left. And what do you notice about this line? Besides, it's not very straight. It's parallel, because they have the same slope. Different y-intercepts. That has a y-intercept of -1. This has a y-intercept of 0, because there is no number out here. That's a 0. So sure enough, these are parallel lines. And the question is, the analysis, where do they intersect? They don't, okay? How many solutions does a system of linear equations have? Absolutely none. Okay? Now, with the same first equation, we're going to now change the second equation again to be 6x minus 2y is equal to 2. Okay? And let's erase the reds here. Okay. Now, sorry, I've got something on my tooth. Really bugging me. Okay, sorry. 6x minus 2y is equal to 2. Okay? What would you do to try to simplify this one? Or, if anything, or would you just start plotting points, or what? Second? Factor out of 2, and that gives you 3x minus y equals 1. And what do you notice there? That is exactly the same equation you have up here. You can rewrite that just like we did before. Y is equal to 3x minus 1, which is exactly the same equation we got here. That has a y-intercept of 1, a slope of 3 in both directions, and there that one is. Let's do our analysis. Where do they intersect? Everywhere along this line. How many solutions does that system have? Infinitely many solutions. Okay? Now, the last question here, 3, what basic types of solution sets are possible for a system of 2 equations and 2 unknowns? You either have one unique solution, no solutions, or an infinite number of solutions, just like we found here. Okay, does that make sense? All right. Neither of you are chemistry majors, are you? Okay, yeah, I remember you. You love chemistry. Okay. There is a little linear algebra applied for balancing chemical equations, and I won't go into that, but if that rings some familiar bells and you want some nostalgia on it, you certainly can. I just made up that word. All right, now let's think back to what we just saw in these three. I've already erased them, and I probably should have kept them. It is possible for a system of linear equations to have exactly one solution, or infinitely many solutions, or no solution. A system of linear equations is consistent when it has at least one solution. Would this system would be consistent? One that I have on the board here. Yeah, it has infinitely many solutions, so it's consistent with the one that was parallel. No, that is inconsistent. It has no solution. And the one that has one and only one solution, consistent, okay? It has at least one solution, okay? So that's what we mean by consistent or inconsistent. If it has at least one solution, which could be infinitely many solutions, it's a consistent system. If it has no solutions, meaning they're parallel lines, that means it's inconsistent system, okay? You will have no solutions. Now, we'll come back and visit those terms where we have bigger systems than just a 2x2, two equations, two unknowns. Those are pretty easy. And we're going to do a couple more of them. So let's move on to example 4. Solve and graph, boo hiss. Let's go back and graph. All right. Each system of linear equations. Here's the first. Let me start with red and then we'll go to the next one. X plus y, that's an ugly y, is equal to 3, and x minus y is equal to -1. What color you want the next one in? Black? Okay, or something else? Blue, okay. Dark blue, okay? Okay. The second one will be x minus y is equal to -1. Okay. Now, it says solve and graph. If you were just asked to solve those, what would you do?
Solve the system.
Second?
Just solve the system.
Yeah, solve the system of equations. You what?
I'll do elimination.
Okay, and how do you do that? Add the two equations together, and what does that give you? 2x. And by adding the two equations together, you lose the y's, don't you? One's positive and one's negative, they go away. And that's equal to? Second? 3 minus 1 is? 2. And that gives us x equal 1. Okay? And then you can go back to either of the two equations and plug in x equal 1. Which one you want to do? Doesn't matter to me. Second one. So you'd have 1 minus y is equal to -1. And what would you do with that?
Same thing. Cancel out.
Okay. I would add y to both sides and add 1 to both sides. So that gives me y is equal to high level math today? 2. 1 plus 1 is 2. Okay, so you've got x equal 1 and y is equal to 2. So there is, that seems like that's what we had last time, wasn't it? Okay. So we solved the system of equations by elimination, by addition they call it, and we came up with 2, 1. Now it says graph them, boo hiss. how would you go about graphing? Let's go back to the red equation, and how would you go about graphing that one? Start plugging in points or do something else?
Start at 3 for the first.
Second?
You start at 3 for the first.
Start at 2?
Start at 3.
I can't hear.
Three.
Sorry.
Start at 3. Y.
Okay. Okay, you're saying y is equal to, is it minus x plus 3? Is that what you're saying? Yeah. Minus x plus 3. I don't hear well, so I don't know. So how would you graph that? Okay. But always start with the point. What's your point? What's your point? Okay. Huh?
3.
Okay, positive 3, 0, positive 3, and then you have a negative 1 slope. So that means you go down 1. Look at that. It goes right through that blue point. Down 1, left 1, down 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. Or up 1, left 1, because 1 over a negative 1 is still a negative 1 slope. So there's the first line. If I could draw straight, it would be something like that. Okay, let's do the second one. Let's go back to blue. Okay. How would you solve that one?
X minus 1.
Okay, I would say x plus 1. X plus 1 is equal to y, right? Add y to both sides. So that has a y-intercept of plus 1. Okay, there we go. And it has a slope of plus 1. And there we have that point again. And that one, and that one, and that one, and that one, and that one. And going down and back, these. Okay. You don't have to draw that many points, but when I draw as poorly as I do, you need every point you can. And there we have it. Sure enough, the one and only one point of intersection is 1, 2. Okay? And that is your solution, which we got this way and graphically. All right. Now, the B one here, the first equation, the red equation, stays the same, but we're changing the second equation. So let's erase all the blues. Trying to get it erase that. I got it. Okay. Erase that too. All right. The second equation now becomes 2x plus 2y is equal to 6. 2x plus 2y is equal to 6. All right. How would you solve that system of equations? Subtract them? Second? How do you simplify? Subtract out of 2? A factor out of 2, okay. Which to me is sort of the same as dividing out of 2. So that would be what?
1x
X,
plus 1y.
Y. Oh, and what do we have? The same equation. Okay? Now, that means same point, same everything, same equation. Infinitely many solutions. Okay. Now, that was a perfectly legitimate and correct way to do it. Here's another way you could have done it. And they sort of wanted you to do this, I think, but it really doesn't matter. If these are your two equations, let me go back and write the red one in red. Okay. x plus y equal 3, and the second one being blue, 2x plus 2y is equal to 6. Typically, if you were doing elimination by addition, what you would do, because you don't have anything that's the same above and below, if you multiply this top equation by -2, then you could eliminate your x's, right? So let's multiply the top equation by -2. And what does that give you? I'll go back to red, just because we were following that. Multiply the top equation by -2. What does that give you?
Negative 2x
-2x
plus 2y.
plus 2y
Oh,
minus 2y. Okay. You're going to come up with some new math on me, okay?
Equals -6.
Equal -6. And then we can add the two equations together like we did before, because this way we can eliminate. But what happens?
Yeah, count before you get
0 plus 0 equals 0, okay? Obviously, you get an identity there. Left-hand side is always equal to the right-hand side, no matter what x's and y's you put in, okay? Now, if that's the case, then we have what we call a infinite number of solutions. If this is always true, no matter what variable you put in there, then then this is the situation that we have here, infinitely many solutions. So anything that will solve the first equation will solve the second equation. Okay, and this is what it looks like when you go to do your solution. You get all zeros, or 7 equals 7, or 45 equals 45, or -3 halves equal -3 halves. You get something that's always true, no matter what value you put in. Okay, that's what we get with an infinite number of solutions. It's a consistent set. Now I'm going to introduce a new word for you here. I don't know when the book will get around to doing it, but I will do it now. Oh, well, whatever. And that is that these are dependent. In other words, this equation, as you saw to begin with, is just twice that. Okay? So this is what we call a set of dependent equations. They will have infinite number of solutions. They're consistent, but they don't have any unique solution because one equation is just a multiple of the other. So that's what we call a dependent system. Okay? Consistent, but dependent. All right. The first one we had was consistent, but independent. Those two lines were independent of each other, so you did get a unique solution. All right. Now let's go to our erasures. And again, we're going to erase the blues. And I think I'll erase this that I did down here too. And I'll erase this part. And this part. And if I could, I will erase that part as well. And I think I did. Okay. I get my new, I can't get my color to come up. There we go. I think, I hope. Yeah, we got it. Now the new second equation is x plus y is equal to 1. Okay? Now, what could you do to solve that system of equations?
I'm just going to say line inspection.
Say that one more time.
I'm just going to say line inspection is not solution.
Okay, he's saying there's no solution. Let's see what it looks like if you try to solve it. What would you do to solve that?
like terms.
Okay. Minus, is that what you said?
I said like term.
Yeah. Okay.
1 in this case.
Okay. I think both of you are seeing exactly the right thing, but how we go about solving this like we did before, well, let's just multiply this equation by minus 1, right? So now we have, yeah, let's see what's going to happen now. Let me get my red back, okay? That would be x plus y is equal to 3, and my blue equation becomes what? Just multiply everything by minus 1. Negative x. No, it's a minus. Minus times plus is minus y. See that minus distributes across is equal to, not 1, negative 1. Okay? Now when we add these, elimination by addition, these add to 0, but those also add to 0. So you wind up on the left-hand side with 0 is equal to what you get on the right-hand side. 2. And when is 0 equal to 2? Never, ever, ever is 0 equal to 2. So guess what? That means you have an inconsistent system. It cannot work. There are no values for x and y which will produce a solution. Okay? So that means you're going to have an inconsistent system. And by the way, this one would be the one that has a, if you rewrote it up here, that would be y is equal to negative x plus 1. So you'd have a y-intercept of plus 1 and a slope of minus 1, which is a parallel line okay, I'm losing my place here. Okay, I think I got them all in place. Inconsistent system because there are no solutions, and this is what it looks like. You get something that's never, ever true. The previous one, you got something that is always true. That's a consistent system, but one equation is dependent on the other. This one, they're independent because they're not the same lines, but they have no solutions, so they're inconsistent. When they do cross and cross in only one place, they're consistent and independent. So the book doesn't go into the dependence, independence yet, but they are getting there. All right. Now let's go back to this slide. There's basically 3 basic types of solution sets that are possible for a system of linear equations, and here's what they say. The number of solutions, we've already said it so many times it's hardly worth writing it down, but I'll do it. I'll go back to black here on my pen. Number of solutions of a system of linear equations. My writing stinks as always. For a system of linear equations, precisely one and only one of these is true. Either 1, the system has exactly one solution, okay, that's the consistent, and I like to add independent case. Okay, one and only one solution. Second possibility has infinitely many solutions. Okay, that's again consistent because it has solutions. Okay? But now they're dependent. The two equations are dependent. One of them depends on the other. Okay? And the third. The system has no solutions. Okay, so it all depends on what number of equations it is. Oh, man. Okay. No solution. This is your inconsistent set. Now, they happen to be independent. Okay. But it's inconsistent because there's no solutions. All right. Any questions on that? What we've already been saying, just demonstrating it further. Now, what if you have a much bigger set than just 2 by 2? 2 by 2s are easy. We're going to find any way you do them, they're going to be fairly easy. But what if you had something that looked like this? I have to be careful that I keep my plug in right. Okay, x minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to minus 4. Excuse me. 2x minus 5y plus 5z is equal to 17. Okay. All right. Now, when you're writing a system of equations like this, here's what I suggest you do. Line up all your variables so they're one over another. And if you're missing one, leave a blank. But also line up the equal signs so they're over each other. I don't have mine quite straight. And then if you have constants on the other side, make sure they line up too. So you have x's over x's, y's over y's, z's over z's, equal signs over equal signs, and constants over constants. That's the best way to go, okay? Now later we'll do some manipulation to that, but for right now, the question is, which system is easier to solve? That system or x minus 2y plus 3z is equal to 9. That's the very same equation at the top. The next one is y plus 3z is equal to 5. And the last one is z is equal to 2. Which of those two systems, and again, these are both systems with 3 equations, 3 unknowns. This one only has one with an x in it, but it's lined up with the other. Only 2 with a y, and they're lined up. And 3 with z's, and they're lined up. Your equal signs lined up, and your constants lined up. Okay? Which of those two you think would be easier to solve?
The one on the right.
The one on the right. Why?
It looks, to me, it seems practical because it kind of slows down the algebra.
Okay, yeah, you don't have as much algebra to do. In fact, you already know one part of the answer. Z is equal to 2. Then you can take this and plug it in here, and that would be what? Y plus 6 is equal to 5. So y would have to be -1. So now you have 2 of your solutions, 2 pieces of the solution. But then you can plug in here, put a -1 in here, a 2 in there, and what would that give you? Positive 2, so x plus 2 plus 6 equal 9. Well, 2 plus 6 equals 8. X plus 8 is equal 9. What does x have to equal? 1. That's pretty easy to solve. Okay? Now, that's called back substitution. If you know what one answer is, and substitute it in the next easiest one, and then sub those into what's the next one, and you wind up with a pretty easy solution. Can't do it here because you don't know what any one of them is. Okay? Now, what if I were to tell, we know the first equation is exactly the same. But what if I were to tell you that the rest of these are equivalent to each other? What that means is whatever solution you have there is going to work here too. Now, you just have to believe me now because there's no way to determine that yet. But we'll see a way to make that happen. Okay? That's where we're heading next. Okay? The system on the right is easier to solve. And this system is given a name. That name is, it's in row echelon form. Now, all right, what does that mean? Here's what it means. The leading non-zero coefficient of each of these equations is the first one you run into. What's that one? 1, 1, 1. Okay, that's the first thing to be in row echelon form. The leading non-zero coefficient, there's a 0, there's a 0, there's a 0. But the leading non-zero coefficient is a 1, and they step forward kind of in an upside-down stairwell type way, that the leading ones are always to the right of the ones above. So here's your leading one in column 1, leading one in column 2, leading one in column 3. They're always to the right of the equation above. That's called row echelon form. Okay? In other words, everything below that, the leading ones here are zeros. That's another way to look at it. Okay. And then you solve them by back substitution. Now, let's do another real easy one. Here's x minus 2y is equal to 5, and y is equal to minus 2. Okay? Is that in row echelon form? Yes, it is. Leading non-zero entry in this one, coefficient in this one is a 1, that one's a 1. And this one is to the right of that one. Okay? Now, and everything's lined up properly. Could you solve that? You already know half of the solution right now. Y is equal to negative 2. What happens if you plug in negative 2 for the y up here? Okay, and what do you get? Y plus 4 equal 5. Guess what? I mean, x plus 4 equal 5. What guess x has to be? 1. So there's your solution. 1, negative 2. We didn't write this one down. What was it, if you can recall? I think it was a 1, minus 1, 2. That was the solution for that one. We didn't have to solve it, but y'all solved it for me. Okay? And this one is 1, negative 2. All right. Now, the term back substitution implies that you work backwards. Okay? For instance, in example 5, the one we just did here, the second equation gives you the value of y, substitute that in and get your value for x. Okay? Let's do, example 6 is x minus 2y plus 3z is equal to 9, y plus 3z is equal to 5, and z is equal to 2. That's that second equation from up there, isn't it? Okay? And we've already done it. We've done our back substitution. Y is equal to 2. They gave us that one. I mean, z equal 2, they gave us that one. Y is equal to negative 1. We calculated that one. And then x equal 1, we got that one. So that's, we've already done example 6. Now, my supposition that I was saying before, if, big F here, if this equation, system of equations, gave you exactly the same solution then we would say that these two systems were equivalent to each other. Okay? So in other words, if these were equivalent, then what can we do to this one to make it look like this to make it so much easier to solve? That's the question. Okay? And that's what we're getting at next. If indeed these are equivalent, and they're telling us they are, then what do we do? Well, here are the three operations that you can do that produce equivalent systems. Okay? Each of the following operations on a system of linear equations produces an equivalent solution. Okay? So these are operations, not like appendectomies or anything, that produce linear or equivalent systems. And equivalent systems are those with the same solutions. Yeah, that produce equivalent systems. Okay, equivalent systems. I think I said linear, but I didn't mean to. All right, here's the operations you can use anytime and in any order you want to. Okay, guess what? You can interchange any two equations. That would be an equivalent system, right? If we just swap these two, it's the same system. It's not the same three equations. Swap these two, swap those two. It doesn't matter. It's the same system. So obviously, exchanging two rows does not change the system. Those will be equivalent systems. That's pretty obvious. Okay, number two. Multiply an equation by a non-zero constant. Multiply an equation by a non-zero constant. Okay. So, if you wanted to multiply this equation here by 1, or negative 1, that would make this an x minus 3y equal 4. You haven't changed the values any. You just multiply by, so any one of these. You can multiply any one of those by a non-zero constant. We do not go around multiplying by 0. If you did that, multiply this equation by 0, you get 0 plus 0 minus 0 plus 0 equals 0. You lose all meaning whatsoever. Don't ever go around multiplying by 0. Okay? Ever. Okay? But you can multiply by any non-zero constant, but you must multiply each term on both sides. And that's a legal move. And you haven't changed the value of the equation at all, or the system of equations. Here's the third one. Now, this one's not maybe quite as obvious. Add a multiple of one equation to another equation. Okay. So, but if you remember, we did that earlier, didn't we? You multiply one equation by negative 2 and added it to the other. That gave you an equivalent system. So sure, we've been doing that. That's called elimination by addition, you know. We did that very thing. So yeah, these three things should produce equivalent systems. Okay? Now, how you do it, the order you do it, and following certain rules, you can come up with row echelon form pretty easily. Now, if you got a book, which I don't see either of you have, but if you do, on page 7 you'll see the lovely picture of Carl Friedrich Gauss, a German mathematician recognized with Newton and Archimedes as one of the 3 greatest mathematicians in history. That's pretty hefty company there. he used what is called Gaussian elimination in his research, named after him, and we still call it that. Sort of the sad news is, poor Gauss, I mean, he's famous for it. The Chinese used an almost identical method 2,000 years before Gauss ever was born. Okay, but no one knew about it because the world was very separate back then. The Chinese were pretty bright. Okay, 2,000 years ahead of Gauss, they were already using the same method. Okay, and we'll use those three operations to do our Gauss elimination. Okay, now let's go back to this same system of equations we have here, and I'm going to show you, and since it's already written here, I'm going to erase it, and we'll get started and use these three rules. Now, I wonder if we need to keep the rules on here, or do you think you can remember? If I need them, I'll come back in. If I need the room, I'll come back and erase. But let's see what we can do. Okay? Now, remember, we're aiming toward row echelon form. And what was true about row echelon form? The leading non-zero coefficient was a what? 1. Okay? Let's look at our very first equation here. Looky there. We've got a 1. Okay? So this is already starting to be row echelon form. The rest of it's not, but that first entry is. Okay? Now, what we want is a 0 underneath it, don't we? Because we want that leading 1 to be stepping back. Okay? So, how could we get this to become a 0? Well, add a multiple of an equation to another equation. So add these two together, 1 times this plus this, and this will become a 0, won't it? So let's do that. Okay? Now I'm going to write over here equation 1 plus equation, I'm going to start calling it just E1 and E2, plus E2 becomes the new E2. Okay? So I'm going to leave equation 1 alone. X minus 2y plus 3z is equal to 9 because it has that leading 1 there. We're happy with that. We want a 0 below it, so let's just add equation 1 to equation 2, and that'll become the new equation 2. So add x to minus x, and what do you get? 0. Add minus 2y plus 3y would give you y. Why not? Okay? Adding 3z to 0 gives you 3z, and adding 9 to minus 4 gives you equal 5. Okay? Guess what? We already have the second equation in row echelon form. This one, the leading non-zero entry is a 1, or the coefficient is 1. This one, the 0 here for the leading 1 is a 1. So already we've got it in row echelon form so far. But we got a problem down here, Houston. We want this to be a 0. Now how do we make that become a 0? Okay, you're heading in the right direction. Let's always use this leading 1 up here. Okay, so let's multiply this one, add a multiple of an equation to another. What will we multiply to this to add to this to make the 2 go away? A negative 2 up here. So let's do negative 2 equation 1 plus equation 3, and that becomes the new equation 3. Okay? So negative 2 times x is minus 2x plus 2x is 0, right? Minus 2 times minus 2y would be plus 4y, right? Minus 5y would be minus y, okay? And minus 2 times positive 3z would be minus 2 times positive 3z. Help me. Say again? No, times, multiply. Negative 6z plus 5z would be negative 6z plus 5z would be minus z, minus 1z, and minus 2 times 9 would be minus 2 times 9, negative 18 plus 17 would be
negative 8.
negative 18 plus 17. Negative 18 plus 17. Negative 1. All right. Good deal. Okay. Now, you got the 0 under there, which is good for row echelon form. But, you see, what we want is, here's your leading 1. Okay? Coefficient of 1. We want zeros below it. Here's your leading 1. We want a 0 below that. So how can we make this one become a 0? Add the two together. So again, I'll write E2 plus E3 becomes the new E3. Okay? So I'm going to write the first one down. We haven't changed that. That's already in good form. X minus 2y plus 3z is equal to 9. And the second one's in good shape because it has a leading 1. Y plus 3z is equal to 5. But the third one, we're going to add those two together, and y minus y becomes, y minus y is 0, right? Y minus y is 0. Okay, we just did that. Let's do this one. 3z minus z becomes 3z minus z. If you have 3 z's and you lose a z, how many z's you got left? 2. 2z, okay. And you have 5 minus 1 is 4. Okay. Now, we're almost there, folks. Look at here. You have a leading 1 here, 0 below it. The leading 1's there, 0 below it. But we don't have a leading 1 there. Now, how can we make that 2 become a 1? Remember our 3 rules? Exchange the 2 equations. Let's not do that. Multiplying one equation by a non-zero constant. What could you multiply this by to make it become a 1? 1/2 is not 0, is it? So we're going to do, and I like to write it like this, E3 divided by 2 becomes my new E3. That's the same as multiplying by 1/2 is dividing by 2, right? So, the new set of equations would be x, equivalent equations, by the way, minus 2y plus 3z is equal to 9. Y plus 3z is equal to 5. And then when you divide the third equation by 2, what do you get? Anybody? Z is equal to 2. And think back on it, that was exactly that other system. That's an equivalent system to this one. That one's in row echelon form because the leading non-zero coefficient is a 1 in all 3 equations, and they step back to the right at least one place each as you go down the equations. And we use these 3 rules to get there, so we know this is an equivalent system. And we've already solved it. Z is equal to 2, y is equal to what? -1 was it? And x equal +1. So there we have our solutions. by back substitution. Okay. Good old Carl Friedrich Gauss and the Chinese before him, okay, came up with that way. And sure enough, our solution set is just like we had it before, 1 minus 1, 2. Okay. Now, they have a illustration, which I'm not about to try to draw, okay, here, that shows. Now, not sure you're familiar with both of you had Cal 3? Okay. Hopefully it was either in late Cal 2 or early Cal 3, you had equations of planes. And a plane is a three-dimensional linear system. So that's a plane, that's a plane, and that's a plane. And this is the first plane, the purple one here. Here's the second plane, the pinkish one there. And the third plane was this greenish one there. And it's hard to tell, but they intersect at one and only one point, and that gives you that one and only one solution. Okay? It's not great, easy to see, but it would be even harder to draw. Okay, so thank you for the graphic. I don't have to do that. Okay? And that place is at 1 on X, minus 1 on Y, and up 2 on Z. Okay. Now, because many steps are required to solve a system of linear equations, it is very easy to make arithmetic errors. We've just seen, I think. So you have to develop a habit of checking your solution by substituting in each equation the original system. Not in your final system, the original system, to make sure you didn't make a dumb error. So let's go back and do that for this original equation. Okay, here's your solution set, order triplet. So let's do 1 minus 2 times minus 1 would be plus 2. 1 plus 2 is 3. Plus 6 is equal to 9. That one works. Let's do the same thing here. The original equation, not the final, the original. Minus 1 minus 3, right, is minus 4. Yes, that works. We didn't use the z because that was the 0 there. Okay, let's do this one. 1 plus 6 plus 10. 1 plus 6 is 7, plus 10 is 17. Yes, that works. So always check your answers if you can. If you've got time and availability and can do it, check your answers, because it's so easy to make a math error. A sign error, an addition, subtraction error, something like that. Even sometimes division or multiplication error, okay? Because you might be adding, sometimes you really should be multiplying or something like that. So that does give your solution. All right. By the way, a little bit on Gauss. By the way, he could be a legitimate paper topic. You didn't write on him, did you?
I started to. I included him. I think he's in there with Kramer.
Okay.
About Gabriel Kramer,
Yeah.
Sometimes when they kind of cross paths, I put that in there.
Yes, exactly. And yeah.
I just thought it'd be cool to include that.
Yeah. Okay. Certainly is. Okay. So you wrote on Gabriel Kramer. So Carl Friedrich Gauss is still out there if you want to do it as a paper topic, but you don't have to. Let me give you a little bit, and I think this story's right. I've read it several times, but I believe he's the one, that when he was like, just 2 or 3 years old or something like that, an unbelievably young age, maybe 5, but I don't think he was that old. His father was a bookkeeper. And so he watched his dad, doing his work. And one day, this really young kid said, "Dad, you made a mistake there." What? He went back and checked his addition, and he had made a mistake. This kid was brilliant. He just watched his dad, saw what he was doing, and corrected him. Okay. He probably had watched him for quite a while and figured out what he was doing. Now, when he got to school, I believe this is the right one. You wouldn't believe this, but sometimes teachers get really tired of their students and want to just have a little bit of quiet time. And this teacher, and I mean just like the first or second grade, was just tired of the kids. They've been making so much noise. He just wanted them to settle down. He wanted a little peace and quiet. He said, write down the numbers from 1 to 100, add them together, and give me your result. Okay? So he thought, keep them quiet for a while. In just a couple of minutes, Carl Friedrich Gauss gave him the answer. Okay? Here's how he did it. Without really writing them down, but let's just do it. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. I can't write. Okay. He wrote better than I did. 13, 14, 15, 16. Kept going, and at some point he got to 100. And before that it was a 99 and a 98 and a 97 and a 96 and a 95 and a 94, a 93, a 92, a 91, 90 and 89, 88, 87, 86, 85, and so on. Notice what happens if you add these two together. What do you get? 101. Add those two together, you get 101. 99 and 2.
Oh, 101.
Yeah. 93, 98 and 3, 101. 101. 101.
So yeah.
Okay, 101. And you could do that back until you got to 50 plus 51. So here he had 50 times 101. And it was 0, 25, 5,250. Obnoxious little kid, wasn't he? Yeah. And I don't even think he wrote them all out like that. He just figured it out. Well, this would be the easy way to do it. He did. That's what makes a good mathematician. Not the person who can grunt through and do it the best. That's okay. It's perfectly fine. But finding the easiest way to do a problem. That's my definition of a good mathematician. That's what we strive for, isn't it? I'm lazy. Okay? Be as lazy as possible. Find the easiest, best way to give you the surefire correct answer. I believe it was Carl Friedrich Gauss did that as a first or second grader or something like that. He could already multiply, obviously, but he did that. All right, anyway. Let's go to example 8. Now, how are we doing on time? Did I bring up my watch?
5 minutes.
5 minutes?
12:45.
Yeah.
At least I got 12:45 time.
Okay. All right. All right. I knew it felt like we were getting close, but sometimes I go right on over. Okay. So let's clear the screen here and do example 8. X1 minus 3x2 plus x3 is equal to 1. 2x1 minus x2 minus 2x3 is equal to 2. And x1 plus 2x2 minus 3x3 is equal to minus 1. All right. Now, elimination by addition, unless you do it very carefully, it's going to be very difficult. Okay? But what we just did, Gaussian elimination, And then back substitution, I think that's going to be our answer. Getting this into row echelon form. So what's the first thing we want? Leading one. We got it already. Didn't have to do a thing. Okay. Then what do we want next? That to be a 0. Now, how do we make that become a 0? We roll by minus 2 equation 1 plus equation 2 and make that the new equation 2. All right, so let's do it. We're using the first one. It already had the 1 there, so we don't do a thing to it. It's just x1 minus 3x2 plus x3 is equal to 1. Okay? Be sure you don't copy something wrong either. Adding, subtracting errors, but also copy errors will really screw you up. Okay, so make sure you got it right. Okay, let's do what we just said. Minus 2 times the first equation, add it to the second equation. What do you get? Minus 2 times x1 is minus 2x1 plus 2x1 is 0. Okay. Minus 2 times minus 3 is minus 2 times minus 3 is minus 2 times minus 3. Positive 6 minus 1 is 5x2. Okay. Minus 2 times 1 is negative 2. Minus 2 is? Okay. Minus 2 is? No, we're not multiplying, we're adding. Minus 4x3. And minus 2 times 1 is? Minus 2 times? Minus 2 times 1 is negative 2. Plus 2 is 0. Right? Now, it's a big boo hiss, because we didn't wind up with a positive 1 there for our leading coefficient. So one thing we might do is divide everything by 5. That would make that a leading 1. But let's not do that yet. Let's go on and eliminate this 1 down here too and see what you get. So what would you need to do to make this become a 0? The bottom x1. Okay, negative equation 1 plus equation 3 becomes the new equation 3. Okay, so let's do that. Minus x1 plus x1 is 0. Okay, minus a minus 3 would be minus a minus 3 is? Minus a minus 3. You're just negating a minus 3. What does that become? Plus 3. Plus 2 would be 5x2, right? Yay or nay?
Yes, sir.
Okay. Minus a 1 would be minus x3, right? Minus 3x3 would be? Yeah, minus x3 minus 3x3 would be? No, minus x3 minus 3x3. Minus 1 minus 3 is? 1 minus 1 minus 3. If you had lost 1 pickle and then you lost 3 more pickles, you lost how many pickles?
3.
You lost 1, then you lost 3 more. Minus 4 x3. Okay? And then minus a minus 1, minus 1, minus 1 would be minus 1 is minus 2, right? Minus 1, minus equation 1, add to that a minus 1, you get a minus 2. Time out, folks. Look at those last two equations. Don't try to get a leading one there yet. Look at these two equations. This says that this very same thing up there equals 0, and the very thing down there equals a minus 2. When does that happen? Never! Whatever this thing on the left is, it's the same in both of those. So let's just call it x4, or whatever you want to call it, is equal to 0, and x4 is equal to minus 2. Can't happen. Because those two are not. The two left-hand sides are the same, the two right-hand sides are not. This is inconsistent, no solution. Okay? That's called an inconsistent system. It has no solution. Now, they did the little graphic on that too, and you have three planes here. There's the top plane is the blue one. The next plane is this purple one, and they have in common a line between the two of them. And then the third plane is this pinkish looking one. Is that what I said? Yeah, that's the third one. And it intersects the blue one there, and those two lines of intersection are parallel to each other. So those two lines never cross, never touch each other, so therefore there's no solution. None, not a single one. And it was that second and third equations that turned out being same thing on the left, different things on the right, so no solution. All right. And unfortunately, I think we are now probably close to being out of time, aren't we?
Yes, sir.
What's that?
12:48.
48. Oh, we are well past out of time. Let me mark. We're going to start next time with example 9. Okay? And by the way, that's what, when you have an inconsistent system, that's what you get. Two things that can't both possibly be true. Okay, we'll begin example 9 next time. Let me put this in place. Oh, we came that close to finishing. I think you can do any of the odds 1 through 5. And by the way, those answers are in the back of the book, but also the answers are found at worked out solutions are at calcchat.com. Remember, that's one of the features of this author. Okay? You can do either 7 or 9. They're both at CalcChat. You can do any of the odds 11 through 23. They're all at CalcChat. You can do your back substitution, 25 to 29. They're all at CalcChat. Graphical analysis, please use a graphing utility. Don't try to graph those by hand, but if you do a few of them if you want to. But they're all at CalcChat, 31 to 35. And then solving systems of equations, you can start working on some of those 37 to 55. If you can't get them all done, especially some of the more complicated or convoluted ones, wait and ask and we'll do those later. Okay? What's that? 1.1. Yeah. Okay. We'll pick up and go from there. All right. Any?
Is this the book for this class?
Let me see it. You may have a new edition.
Oh, I need it. That's what they had in bookstore.
Oh, you do have a new edition. I've got to get a new one. See, I'm supposed to. Oh, absolutely, absolutely. Hardly anything changes. They just do new editions so they can sell new books. So the publisher only makes money on new books. They don't make money on used books. That's why every 3 or 4 years they want the authors to come up with a new edition.
So the same information is different color.
What's that? Yeah.
Same information is different
And
color.
sometimes they'll change colors, or they may add another little something. I've got to get me a new one, so I'll then update. Unfortunately, I'll be updating syllabus and all sorts of stuff, but I also see if there's anything. Well, they don't have PowerPoint, so it won't be that. So I'll try to get me one so I'll be on the same page you will.
Okay. All right.
Good deal.
All right. All right, thank you, Dr.
Uh-huh. We'll see you Thursday.
Yes, sir.